Okay, Jesus. Great to have you with us. How you doing, mate?
Oh, very, very, very good. Super excited to be here, and yeah, looking forward to it.
Good. I'm really glad we finally made it. The way I start these things is just reading a couple of lines of your resume, because I want to ensure that what we know of you is correct from a path and academic perspective. So you're currently assistant professor at the Department of Chemistry at University of California, Davis, right? You did your undergraduate work in Puerto Rico, at University of Puerto Rico in Cayey. After undergrad, you worked in industry for a couple of years, right? With Beckman Coulter, if I'm not wrong. And then you started your PhD at the State University of New York in Buffalo. With Sarbajit Banerjee, right? And then you did a postdoc in Caltech before then landing your current job at Davis. Is that correct?
That is all correct. Yes, fantastic. Yes, that was the journey.
It's a great start if I take this correct. And so this is the journey, and it's an interesting story, right? First of all, there's movement across countries, right? Yeah. Well, Puerto Rico is technically part of the U.S., so you're not really abroad, are you? But culturally, I'm sure there's quite a difference between Puerto Rico and New York or California, right? So I'm sure there's something there that I'd love to investigate. Well, why don't we start? Why don't we start there, really? So. You're the first guest from Puerto Rico, so I don't know how is the scientific community over there? Is it something lively and rich? Is there a lot going on?
Well, let me tell you, I want to say that yes, there is a very strong scientific representation in Puerto Rico. Just a rainbow of sciences and engineering disciplines being properly represented, not only through independent scientific research, and the University of Puerto Rico is about 10 to 11 campuses, but as well as the Ana Jimenez universities as well. And every year, I want to say there's just more and more progress, not only because it's been a work in progress, but also because of the nature of how science has become very collaborative. And what this means is that there's been a lot of investment from the National Science Foundation, NIH, all sorts of funding from the US to try to provide the resources to the universities of Puerto Rico to establish connections with scientists in the mainland, but as well as to nurture some of the independent scientific efforts there. Of course, I've painted a very ideal and beautiful picture. There's a lot of added bonuses and challenges that Puerto Rico is facing to try to maintain all of the rich discovery and scientific progress that they've made over the decades, but it's still lively and going. I, for one, have not only collaborative projects with professors like Yomaira Pagana in the University of Puerto Rico and Maya West, but I also have the great opportunity of recruiting students as well, going to Puerto Rico at least once a year, presenting, bringing students to do summer internships at UC Davis. So yeah, I mean, there's just a lot of really impactful science going on. Great support. There are some challenges there, and hopefully, as time continues to progress, we can figure those out.
What are those challenges?
Well, I want to say that unfortunately, there's been a lot of political influences that unfortunately are not as progressive and positive as you would hope for. When I say political influences, that basically impacts administration, and if it impacts administration, then it's just a snowball effect.
Availability of resources for the scientific community and all the rest, right?
Exactly. So it starts there, but it doesn't really impact the desire, the creativity. I mean, All these professors in the universities of Puerto Rico are just trying to be creative and trying to make $1 out of 15 cents. Let me tell you, they're just figuring out ways and how to still push all these scientific efforts.
This is interesting, right? The, constrained resources sometimes are not a limitation. They actually stimulate creativity, right? They even give you an edge, which seems counterintuitive, but it's often the case. And that's why you have very often great science coming out to places that are surprising at first sight, but it's probably spans from this, at least a little bit, isn't it?
Mm-hmm. No, definitely. Necessity is the mother of invention.
Yeah.
Right. And Puerto Rico is a great example of science is just figuring out ways. I want to say that it's also been because of the U.S. Puerto Rico connections. Right. Now we're in this position where a lot of the students, a lot of the undergraduates who have come to the U.S. to pursue graduate school, or high school students who have pursued undergraduates and have gone to the academic journey or just scientific journey, now they have positions like myself in universities, and right, so it's become this distribution of knowledge that it's all over the U.S., which is positive in a sense because we could figure out ways on how to support and further encourage what we would like for it to happen in Puerto Rico. But then there is also a little bit of a challenge, right? Because a lot of the knowledge has moved away from the island, right? But I see it as an opportunity, and not only myself, a lot of my colleagues from Puerto Rico who are in academic positions or in industry positions, we've figured out ways on how to just establish a network and really have everlasting support to the efforts that are happening on the island of Puerto Rico.
I can see how you are attached to your land, right? To your roots, which makes sense and it's perfectly understandable. The way you speak about this is like, it seems like you feel the need to give back. So do you feel spoiled where you are at the moment compared to where you come from?
Yeah, a lot. And then I catch myself sometimes, making comments where I'm like, wait a second, just remember where you came from for a minute, right? I mean, you've had the great opportunity to sort of maneuver your way across a couple of challenges, and now you're here. I have to sometimes always try to reconnect with that, right? Because it gives me, it allows me to have a well-defined purpose, and it's just fire that sometimes one needs, considering all the challenges that one faces, right? But yeah, I mean, I feel of responsibility sometimes where I understand what are the challenges that my community faces. And me being from that community who, with a lot of support, it took a village, who figured out a path towards having the shot of not only working something that I feel passionate about, that I know that in the big picture scheme of things will have scientific and technological impact, but at the same time, I have the great fortune of having societal impact as well.
Yeah.
So I try to use this platform to do that as much as possible.
Is this what you're trying to do? It's trying to help people to follow a path similar to what you've been privileged in a way, or lucky, or probably even good, of course, not probably, certainly, right? So is he doing the same and it's giving other people the same opportunities that you had, and obviously they would need to earn right their chances and make the best of the opportunities, and that's for every one of us. But is that your goal?
Yeah, and I mean, through that goal, understanding that everyone is different, right? Everyone will process information and identify opportunities in their own style, and that's okay as well. Right at the beginning, when I began my career as an independent scientist and and as a academic advisor, I felt like, okay, this should be pretty straightforward to understand, right? I mean, these are the sort of these are the dots that you have to connect. And if I just convey it, it will be processed instantly, and it's going to be straightforward. But no, and that's okay, right? Folks, everyone has different. I like to tell myself sometimes students or folks in our community will be ready to receive the information that you are providing. Sometimes they won't, right. And I should just try to maintain a conscience of that, right? Makes
perfect sense. How do you structure your sort of social involvement and this work you're trying to do? Is it more of a personal initiative? Do you leverage any sort of structured organizations and try and do it? How does it work? Where do you get the funding? Because I'm assuming you also need that type of support.
Yeah, so it has to definitely tie in with. It so happens that I have the privilege of being a professor in an R1 institution that cares about research, cares about teaching, cares about broader impact, and not only from an institution level, but funding agencies across the U.S. also have all sorts of initiatives and opportunities for one to be able to provide ideas on the matter. Yeah. So I have to basically align. It's almost so. Just to give you an example, we have a summer undergraduate research experience over the summers that is funded by the National Science Foundation. Right. One of the missions of that program is to have broader participation of students in STEM. Right. With an emphasis in figuring out ways on how to encourage participation of students from minority communities or underrepresented communities. So because I've already gone through the path, I have a relationship with the University of Puerto Rico. One of the things that I do is I try to go to Puerto Rico at least once a year, interview a couple of students, and every other summer they'll come to the university and do research, maybe for the first or second time. Right? That little, it might seem little, as I describe it. It's really not. It's really not, right? Because the student comes in, gets exposed to research. Often something ignites in terms of an idea. Perhaps even that is the gateway for them to see a possibility of them being a scientist.
Exactly.
Okay? Then the next thing you know, they're joining a graduate program. It could be at UC Davis. It could be anywhere in the country. The point is that they're doing it. And now, if we could do this every other year or every year, if you look at the marathon and not the sprint, you have this opportunity to, with time, build a breadth of trainees that will potentially be doing, what I'm doing or better.
Yeah.
Right?
And you show them what it is, right? Because the challenges in life, the biggest one is that you don't know what you don't know, right? How do you know what it means to do research if you have never seen it, right? And people need inspirations and mentorship. Everybody wants to be a footballer in Europe, right? Because they see all these successful footballers. They're beautiful athletes. They do incredible things on the field, right? I'm sure it's the same for the sport culture in the U.S. Whatever, American football, basketball. You need some examples like yourself in the scientific community to just kind of go after it.
Let me tell you, Paolo, I tried to do baseball, but I couldn't do it.
Well,
so I'm a scientist now.
So that was your second choice. Yeah. You would have made more money as playing baseball. Sure.
I know. I was just not good at it. I tried.
Anyway, this is all very noble, Jesus, and I, you obviously have a great personality, and I'm sure these guys can get a lot of inspiration from working with you and interacting with you. We don't do enough of these things, right? I'm saying we. Maybe you have more to give than I have. It's I wish I wish there were more people like you. You're not forgetting their roots and investing time and effort, because it takes time and effort to do it, right? And courage, I would say.
It's that is essentially one of the challenges, right? It does take time, but with a little bit of creativity, I feel like it could be done without jeopardizing scientific novelty, without impacting, scientific output. Would usually that is, perhaps the concern or intimidation that others may have, right? You just have to figure out a way to how to basically align the initiatives, and the next thing you know, you're doing it, right? You are training the next generation of students, and it so happens that these students are coming from marginalized and perhaps challenged communities, and they are getting involved in top-notch research. They have the creativity, they have the desire. So you just align all these all these opportunities, and the next thing you know, yes, the high impact factor papers are coming out, you're getting funded, students are getting trained. It can happen, and it's happening. It's not only in my group. I just have so many examples. I come from all sorts of different groups that mentored me and showed me that actually it is possible, right?
Yeah, and that's where I want to go, because we have been speaking quite a lot about what you do for the new generations, right, and how you inspire them. But there's been mentors and important figures in your own path. And I like to actually try and reconstruct it, because, as I said at the beginning, you have an interesting story between Puerto Rico and different parts of the U.S. And I learned now that you weren't quite good enough as a baseball player, so maybe science was your second choice. But how did you even bump into science? How this passion started?
Yeah, so I mean, I say that it was a mixture of great teachers, of course, those teachers that are just go above and beyond, with little to no resources, again, give us opportunities to try to understand how impactful it could be to understanding science and implementing it. So there was a lot of key little programs happening, at elementary school, junior high, and whatnot. But if I had to pick one program, it would have to be the Math and Science Upper Bound program. And this program, back in the days, gave a 15-year-old like me an opportunity to experience research at a university in the university at a university at the U.S. So the program specifically focused on first-generation low-income, underrepresented students in STEM that come from New York City, Puerto Rico, and Virgin Islands. And they took us in, and for 10 weeks, they gave us the opportunity to experience what college life is all about. It's there where I got exposed to the world of environmental research for the first time, actually. We used to go to creeks and use the population of microinvertebrates to establish water quality. So that was sort of my first. It was my first realization. Like, I could physically understand, that things are perhaps contaminated, and in terms of natural ecosystems and whatnot. And then I connected that throughout my professional career, connected that through some of the challenges that I faced in Puerto Rico with hurricanes and access to clean water and energy and all that good stuff.
Let's say, I can actually do something about it, right? With my work.
Exactly. So then, going back to the whole mentorship support, at early stages, it was the teachers, it was the coaches, even the baseball ones, okay?
Sure.
It was the teachers and the coaches back in my little town in Juncos, Puerto Rico. All the support, all the promise that they saw, in me when I didn't even really knew what I was, showing. I was just showing the desire, the passion, the interest. When you see that from a student, as a teacher and professor, it's unavoidable. You want to support this student to figure out their own path. So yeah, then that geared me to programs like the Math and Science Superbound, and then fast forwarding to a career starting with a PhD in University of Buffalo. That's where I met Professor Sarbajit Banerjee, where he was a first year professor starting a brand new laboratory.
Yeah.
And here I come with a little bit of experience on industry, really falling in love with the fact that the topic that Sarbajit really wanted to pursue was the design of nanomaterials for all sorts of energy applications. I did not know nothing about it. Okay, only thing I knew, Paolo, is that I remember seeing for the first time an image from a scanning electron microscope, and seeing those beautiful little crystals, and knowing that I can manipulate the actual geometry. I can manipulate the chemical makeup of these particles. Sarbajit said, yeah, I mean, this is what I was trained for. You could learn how to do this. And I said, okay, you got me. Where do I need to sign? And he took a risk. He definitely took a risk, right? He saw a passionate and dedicated person, but I had little to no experience. But it was thanks to mentorship like Sarbajit, with a lot of patience and dedication to build me from the ground up, is what ignited now the opportunity to then go to Caltech and actually do a brand new lab as well, again, funded by the Department of Energy, which at the time was the Joint Center of Artificial Photosynthesis. And that experience there not only opened up the opportunity to be mentored by renowned scientists like Professor Nate Lewis, also Bruce Brunswick, but because of the idea of the Joint Center of Artificial Photosynthesis of bringing in the best of the best in synthesis and theoretical modeling and engineering and doing life cycle assessments and putting them all under one roof to actually try to figure out how we could put a device that could do that could split water better than current crops. And that right there, that was even a bigger opportunity for me to bring in even more mentors. Because of the collaborative nature of the project. So, in every step of the way, there was very key guidance and support and mentorship, but it always began with these mentors that are still part of my network to see the promise, right? To see, okay, he might not know perhaps how to do vapor liquid solid method to do a well-defined thin film, but that could be trained, right? Desire, passion, dedication, work ethic. These are traits that if you already have them because of your of the experience you had in the past, then that could be leveraged.
And when you have desire and you go through a path which is not the easy one, right? You go through challenges. You need to train yourself to overcome them, to stick to it, keep fighting, right? That's what you need in science as well.
Exactly.
And then when you start being in that environment and you have so many powerful mentors around you and you are in this surrounded by brilliant people, then you breathe it, right? And it becomes natural, so you start thinking a way. Just getting there is tricky, right? Once you get there, and then obviously if you have the capabilities.
That right there, the tricky part, it is tricky, right? Because of the journey that I've had the opportunity to endure, getting exposed to such talent, yes, you could breathe it in. And it's contagious for sure, but obviously like you could imagine, right, at the beginning there is obviously an energy barrier, right?
Yeah.
Right. You're sort of like, okay, oh my God, I'm here next to all these brilliant folks, and now
Imposter
I need
syndrome. So what am I doing here?
exactly. I'm like, what are they? Do they really know who they have here? No. It takes a little time for you to actually understand and say, okay, wait a second. This is my footing. This is what I bring into the table. And now, once that's clear, then it's just harmony, right? Then everything just is really fluent in terms of being able to put everything together and have actually meaningful impact in terms of the science.
That makes perfect sense. And then eventually, you went through it, and obviously did a great job, and then you started, a new lab for the third time, your own this time. By now you have like a PhD in setting up new labs. It's like an extra one, isn't it?
Exactly.
Was it getting easier time after time, or not?
No. No.
It never does it?
Not at all. But it's every time I just gather myself for a minute and think what the opportunity that I have of building a team of students who are really passionate about energy and environmental science, and also really passionate about what I felt about the reason why I fell in love with materials chemistry in the first place, which is that opportunity of manipulating matter through chemistry. And not only it makes for beautiful crystals and perhaps sophisticated manipulation of chemical coordination, but it also has an applicability, right? These changes that we're doing on surfaces of materials, these composition modifications, this manipulation of electronic structure, have impact on physical chemical properties, right? That could be implemented and applied in the world of catalysis and energy storage, selective absorption of contaminants from water, right? And now I have a lab dedicated to that, which is, every time I say it, I have to take a couple of seconds to realize it, right?
Yeah. Well, it's great, and you should be proud, and it's nice to be down to earth and say, yeah, sometimes I need to pinch myself, say, oh yeah, I'm really doing this. It's great. I encourage you to try and stay like that. You probably won't, but it's great, and it's lovely to see. It's probably time to get into it, right? Shall we describe? You said it, right? You're a material scientist, and it's material science is fascinating. It's one of the biggest promises of chemistry, right? If you think about everything exciting is going on in chemistry at the moment, you probably have the interfaces with biology and more of the pharmaceutical applications and biotechnology aspects. That's a very exciting field. Material science is another one, isn't it? But it's also a tricky one for the more traditional chemists, because it's so multidisciplinary, isn't it? So you have the chemistry, or the inorganic chemistry, or it could be metal organic chemistry or whatever, but you have the physical sciences, you have the engineering aspect, and then all the plethora of applications. What is your angle? What can you describe what you actually do, and going into some of your scientific details?
Yeah, so I mean, one of the things that we notice specifically when we were looking at what other levers of molecular control we could put together to synthesize solids to perform specific electrochemical reactions, we noticed that for the past decades, we have a fairly good understanding of molecular systems that could allow us to perhaps split water into hydrogen, or even convert carbon dioxide to methanol. And we might have monometallic surfaces that could do that very well. Things like copper, like silver, and gold. Now, one of the things that, because of all the breakthroughs with characterization, specifically spectroscopy and microscopy, Now, if we compare now to perhaps a couple of decades ago, now we have the opportunity to monitor these dynamic processes, meaning these electrochemical reactions. Right? We have the ability to look at the interface between a solid and a liquid that is perhaps under an electric field and try to understand how the chemical makeup of that surface is changing, how the environment of that liquid electrolyte is impacting that environment. And if you take those all these pieces together, that made me think and say, well, we know we have solid catalysts and we have molecular catalysts. Is there an in between? Can we, or not only that, can we have inspiration from what all the transitional metal complex community has been able to do in catalysis? Can we take inspiration of that and try to encode that those design principles into solid, crystalline, extended structures? So that leads us to us basically saying, well, what is the current state of the art? I mean, what are perhaps some of the examples out there of metallic surfaces that have metallic solid surfaces that perhaps when combined with something like sulfur or with oxygen, the local geometry and local chemical coordination is perhaps a little bit similar to what a molecular complex is, right? And that leads us to the world of metal organic frameworks. That leads us to the world of Chevral Phases, right? Which is a composition space that we've been exploring, for the past couple of years through the development in our laboratory. Because when you look at them, it's essentially these little cluster units that are all within the extended solid structure, shared through sulfur bonding, but you have the little cluster unit, right? Which is sort of analogous to perhaps cluster units that you see on single molecular complexes. So that's been the angle. The angle it's been, I think that we can definitely get inspiration from the molecular complexes in terms of being able to do selective electrochemistry, electrochemical reactions, and we can use some of the known and there's the need to establish new, perhaps nanochemistry synthetic pathways to manipulate some of these solid crystalline materials. It's really important that we do this because one of the major downfalls of solids in electrocatalysis is that it's really hard to know what is the surface termination that you're actually exposing to the actual liquid electrolyte when you're trying to do.
So are you saying the reaction only happens on the surface of the solid material, isn't it? And then, because that's what's in contact with the solution, with the outer environment, isn't it?
Exactly. That's one, but not only that. Sometimes we struggle to know precisely, as we're doing the electrochemical reaction, precisely what is that surface termination. But the beautiful thing, the beautiful opportunity is that because of advances in microscopy and spectroscopy, we perhaps now are in a position to have the spatial and the temporal resolution needed for us to be able to go at the interface and monitor in real environments these electrochemical reactions. I mean, obviously these experiments are challenging.
Sure.
It's stuff that perhaps to a certain extent you can't really do in a bench, in your bench laboratory. But that's when a key this goes back to the collaborative challenge that the interdisciplinary challenge that you mentioned. That leads us to the opportunity to collaborate with national laboratories. So for instance, our lab takes great advantage of being in close proximity to Lawrence Berkeley National Lab and the Stanford Linear Accelerator Laboratory. So I have students at least 3 to 4 times a year driving down and working side by side with very talented staff scientists in figuring out how we could design the electrochemical cell. What do we need to do to have a proper electrode so we could then do these experiments where we're monitoring both how composition is changing as a function of applied potential, and basically have sort of the electrochemical response as well as the spectroscopy all working in synchrony. So this is more of the inoperando characterization field that has become really there's still a lot of work to do, but it's right at really close to our fingertips to mainstream it.
This is very modern science, isn't it? Because it's not a chemist doing chemistry, and start with chemistry and do chemistry. This is a chemist going out there and trying to speak a different language to people coming from a different background. How challenging is that?
It is. I think that I was actually, because of the way I was exposed and developed with Sarbajit at SUNY and with Nate and Bruce and others at Caltech, I've been exposed to how to build collaborative teams, how to understand the diverse audiences that we have to talk to, sometimes as just presenting your work, but sometimes as just figuring out how we could identify what are the hypotheses and the main questions that we're trying to resolve, regardless of who is in the audience. If it's an engineer, if it's a chemist, if it's a physicist, it's still not resolved. I mean, it's still a challenge, right?
Course.
It's still,
of course.
But I think that through my PhD and postdoc, that was sort of the norm. That was part of, the approach was almost like, okay, we could take the projects to this level, but now for us to be able to, answer a couple of the other aims, we need to bring in people, right? And I think that for me is really natural, just because I was developed under that environment.
Yeah, you came up with this mindset, right?
Exactly.
And if someone's probably coming from a completely different background, just working on their synthetic chemistry for years on end, and then at some point gets exposed to this sort of way of working, is really tricky. It's
definitely possible, but I agree with you. It can be it can be a little tricky, but definitely, if one has the desire. I mean, everyone is reading the enormous amount of scientific output that is out there, right? When you look and you read these scientific papers, you see that there's the need for us to be able to have technological realizations on some of our ideas. We need to collaborate. It's what allows us to perhaps cut the timeline from 15 to 20 years to hopefully 5 to 10.
And it's the collective human brain. It's how the species evolved, really, right? It's putting every little neuron we have as individuals together. You make a bigger brain, isn't it? That's what it is. We have been programmed for that. We need to just remember to do it. I have a lot of questions. I'm overly curious too often, but anyway, there's obviously your research is very complex for the reasons you just described. So you focus on some of these nanostructured materials, mostly on these chalcogenides, and you mentioned the Chevral Phases, but I'm sure your interest is probably broader than that. So the type of work, the way I see it from my perspective, can go in multiple directions. You obviously have the understanding of the nanostructure of the material and how you can actually make them and alter them. Then there's the synthetic, methods to get them efficiently and reproducibly. Then there's the characterization aspect, and then there's the application. What you can use these things for. Are you running all these lines of research? Are they obviously they are all interconnected, right? What is your main focus, or is there any main focus?
Yeah. So I would say that when I talk with with students who are about to join the lab, I say, okay, we have three broad categories. So we have the synthesis aspect of our lab, we have the electroanalytical aspect of our lab, and then we have the spectroscopy aspect of our lab. Now, the synthesis aspect, just like you described, it allows us to impact composition, electronic structure, morphology, have a saying of what is the surface termination that we're exposing on these electrochemical reactions that we're trying to do. Then that leads me to the electroanalytical side, where what we're doing is using electrochemistry to have some initial understanding on perhaps some charge transfer properties that we're seeing of our materials as a function of manipulating composition and electronic structure. Right now, these are the type of data that we get is cyclical thermograms, how the current is changed as a function of potential. I mean, it could obviously evolve way more than that, but the analytical part is we do this in synchrony with gas chromatography and nuclear magnetic resonance. And what we're trying to do there is we're trying to monitor how we, as a function of potential, and how we are perhaps converting small molecules like carbon dioxide and splitting water, how we are impacting efficiencies and selectivity as a function of an electrochemical environment. So we could do that by looking at the headspace of an electrochemical cell through gas chromatography, the liquid phase through NMR, and then essentially make calculations and determine what is, how efficient are we doing this conversion process from carbon dioxide, for instance, right? And then the spectroscopy part, it somewhat divides in two. There's the spectroscopy that we use to validate our synthetic successes or failures.
Did I make what I wanted to make, right?
Exactly. Yeah. But then there's the spectroscopy, as I was describing earlier, that with a little bit of TLC, as I like to say, tender loving and care, we can monitor the electrochemical process, right? So the information that we're getting from spectroscopy and from the electroanalytical is giving us insights towards the application. So that's how I connect the world, how I connect each of the worlds. Now, of course, there are moments where, we've hit perhaps a wall or a limitation of our understanding of what's happening. And that we are the first ones to basically understand that we might need perhaps DFT calculations to try to understand some of these reactions. And we're really actually fortunate that we have established collaborations, like, for instance, a really strong collaboration that we have with Charles Musgrave over the University of Colorado Boulder, with incorporating theoretical calculations from experts like the Musgrave group. What that allows us to do is not only have theoretical calculations that sort of give us insight of what the potential electrochemical mechanism is, but they also have ways of telling us what could potentially be synthesizable.
Right.
What us even perhaps trying in the reaction in the laboratory. Although if you ask my graduate student Jessica, she's always a step ahead of the theoreticians. She's a living machine learning young scientist. I'm telling you now. Yeah. But yeah, that's how we divide it. Exactly.
That's a very cool one. I'm just in my brain trying to decide which of the two directions I wanted to pick. I want to pick. But anyway, let me start from this. I'm coming from an organic chemistry and biochemistry background. So my knowledge in this type of materials is unfortunately very, very limited. So I'm afraid I incur into the risk of asking stupid questions. Anyway, I know very little about how you make this type, how you control this type of material. Can you tell us? And I'm sure there's a number of different methods and examples, but for my benefit and the benefit of the audience, would you comment on some of the more important ones, maybe the ones that you like particularly or that you guys use?
Okay, I'm going to comment on one. We'll see how it goes. But the one of the favorite ones is because it has a really nice story. So one of the synthetic techniques that that is one of our go-tos for synthesizing multinary chalcodonite solids, solid state synthesis of multinary chalcodonites, is a hot pocket microwave. literally. And so what we've been doing is we've been using the opportunity to use microwaves to obtain high temperatures at a rapid pace, and then do rapid quenching following the heating process, to actually have really great yields in terms of purity and establishing the crystal phases that we want. Now, the way that this is done is this is a solid state reaction. So all of our precursors are solids, and we have depending on the end goal, we have a stoichiometric amount of either monometallic species or binary species before we actually do the microwave reaction. Mixing with a ball mill is actually really important. So we take all the solids, we mix them very, very, very nicely. Then after that, we have sort of this. We have our way for us to be able to introduce the very nicely mixed solids into a quartz tube, and we use graphite as a susceptor that allows us to even go to temperatures as high as 1,000 or 1,100 degrees Celsius.
Okay.
And this is all through a Panasonic microwave, and
it's like
and Jessica,
normal consumer type.
Yeah,
microwave.
Yeah, and actually, so what my graduate student Jessica, she's constantly bugging me and saying, you need to talk to Panasonic. You know how many microwaves we've used in the past 4 years? They need to sponsor us. No, I'm just kidding. No, but it's true. No, but because it's a really nice way for us to be able to get to high temperatures.
Right.
In a
localized way, right? Very specific.
In a localized way, and in a rapid fashion.
And it works because you use paramagnetic materials, because this is solid phase. So there's no water in there, is it?
Exactly, no water, and then the actual graphite allows us for us to get Joule heating, essentially. So the microwaves interacts with the graphite, ignites Joule heating, and then we have a saying of reaching to really high temperatures in a timely fashion.
So basically, the way you control the the structure, the nanostructure formations is through temperature, very fine temperature control, and time of the temperature, and all these sort of things.
Well, that's a really good question, because thus far for Chevral Phases, what we've been so if you do a basic solid state reaction with microwave to do the for instance, the copper intercalated molybdenum 6 sulfur 8 Chevral phase, what you would end up is what we like to say in the solid state community with the bulk material. So we don't have a saying in the morphology with those conditions, but we do have a saying on having the proper chemical makeup that we want as the end goal. However, to impact morphology, one of my graduate students, who's not a postdoc at Stanford, Joseph Perriman, he was able to figure out that by having sulfur deficiencies, we could trigger preferential nucleation of wires of, instead of molybdenum 6 sulfur 8, molybdenum 6 sulfur 6.
Uh-huh.
So and obviously this is still a work in progress.
So that is
terms of monitoring the crystal.
That's the way you control it. It's also through your mixture, solid mixture compositions, and
Exactly.
And
but that's only
how
one
well you
way.
mix as well, I suppose, because these are localized events. So you really need to have this sulfur in that specific nano scale to have the reaction occurring, right?
Yeah. So what was the question? How did what?
No, I mean you need to ensure that you mix it properly. So you really need to have the right atoms in the localized space where the reaction has to occur. Otherwise, it just doesn't happen.
Exactly. Mixing in solid state chemistry is
that's
actually
a nightmare in organic
imperative.
chemistry. When you need to blend solids, this is the nightmare of any chemist. Yes, particularly in bulk.
And it has led to a reinvigorated field. Actually, it's called it's being highly pushed in groups all over the world, which is mechanochemistry, and where if you could achieve a system that allows you to do, finite mixing of solids, but at the same time heat them.
Oh, okay, I see.
Then you have the levers of control on these basically both conditions, and that has allowed a lot of discoveries of, for instance, metastable phases of that otherwise it wouldn't be accessible through traditional solid state chemistry.
I understand. This is so fascinating to me because it's so different from the new, the normal, which from my perspective, world of chemistry in solution, right? Because everything becomes homogeneous once it's in a solvent, but it's not like that in the solid phase, and it's really cool and interesting. So you mentioned a few applications, right? There's environmental science. The carbon dioxide reduction is particularly attractive for obvious reasons, and I'm sure there's more, right? There is one thing that I had in mind. This is probably making electrochemistry and even photocatalysis interesting, very attractive these days, because chemistry is at the eve of a massive change of paradigm, isn't it? All the chemical feedstock has been coming for decades from oil, so we are starting from fully reduced carbon, starting materials. This is going to change, and this is not how nature does it. Nature starts from fully oxidized species, and going in reduction reactions. This is what you guys seem to be doing very well. Most of organic synthesis, most of synthetic chemistry is actually thinking in the opposite direction. Mm-hmm. So this is maybe getting a bit too philosophical, but I can see why this is a very hot topic, and to me it's going to just become hotter. What's your take?
Yeah, I think that not only because of all the opportunities we have in terms of selective, conversion of feedstocks that we know they have major implications to the environment, but also there's all this renewed interest in doing essentially electrosynthesis, right?
Yeah.
And then add to that the fact that all these breakthroughs that we've had with renewables like solar and wind, right? Now we have sort of a much more promising picture of being able to use cheap electricity to do electrochemical reactions.
True, because
right?
Where the electricity is coming from is a key point here, right?
Yeah,
because if you need to burn coal for it, then
Yeah. So I think that some of these pieces, not only from the fundamental chemistry standpoint of view of all the different options that we might have, if we could continue to try to understand how to use electrochemical processes to do catalysis and synthesis of small molecules, but where the electricity is coming from, like you mentioned, it's definitely key. And in the world of photoelectrochemistry and photocatalysis is still a very interesting and potentially groundbreaking idea. How about if we could just do an all-in-one, where instead of having a photovoltaic giving our electrons and wire that to an electrolyzer, how about if we could actually do all the both processes in one system? That, of course, is not a new idea. That is something that has been. I described a project that invested the Department of Energy invested substantially on, which was the Joint Center of Artificial Photosynthesis, and try to figure this out on how we could make this device that indeed could be could do this process, both selective, stable, and with materials that are economically viable as well.
Yeah, and easy to make, right? And hence, all your progress and the research on how to make these materials in a reproducible way.
Yeah, and you would think, right? You would think, right? It's okay, right? We're splitting water. How hard that could be? Well, yeah, it's it is, and
there's a reason why there's so much water.
Exactly. Exactly.
It's not that easy to split.
Yeah, and it's it's been decades of efforts from amazing scientists trying to to put all the pieces together, fundamentally understand it to the level where it becomes technologically viable. I think that from the electrolyzer standpoint of view, there's been a lot of very interesting new promising companies doing really cool work. Like one of them is, for instance, the company 12 that is right next door of us, where they are building electrolyzers to take carbon dioxide and convert it to carbon monoxide and formate and other interesting small molecules that can be liquid fuels or value-added products. But
to me, that is where chemistry is going. In the future, that's what we're going to do.
Yeah. So it seems really exciting. There's a lot of, going back to what we were talking earlier, there's a lot of initiatives from the fundamental science, from the technological innovation, investment and interest from the government and whatnot. There's a lot of things that are aligning at the moment to make great strides in this field.
You need the economic incentive for a field to thrive. You can be scientifically as interesting as you want, but if there's no attractiveness from the money perspective, it's just not happening, is it?
Great.
So you're lucky from this perspective. You're probably in a hot area which is getting hotter.
Well, I don't know if it's funny because I remember saying there was a moment where it was not as hot, and I was like, man, I wish there was a little, it was a little bit more support. But now it's like everyone, right? I mean, there's just a lot of interest. No, but it's a really good thing. To try to answer very impactful as well as questions that are of interest to folks who are really to invest in us to be able to get these answers. So it's a really good time, for sure.
Let me close this circle between the fundamental science and the economic incentive. You mentioned that for you personally, the thought that your work can have a real implication is really important, right? You have this attitude that you want to give back, and you want your work and time to be meaningful, which is understandable. Are you usually in your project starting from the more fundamental understanding of some of your materials and then looking at the application, or is it the other way around? Are you looking for an application and then you go and manipulate the fundamental states of your material?
I think that the way that that my team, the way that we've put together this lab, thus far it has been, we understand what are the necessities in terms of being able to use heterogeneous or inorganic solids. We understand what are the needs in the field in terms of how we could use the chemical makeup of these solids to do specific reactions. Specifically, like we mentioned, CO2 reduction has been a very strong. We've had strong interest in trying to synthesize materials that allows us to get that reactivity.
Of course, yeah.
Right. So that has been a big way on how we've structured our laboratory in terms of motivation and in terms of the fundamental aspects behind our materials. There are moments where we have a fundamentally interesting perhaps elucidation of a material that not necessarily not translate into a device functionality, but we see it as we see it as an initial steps,
of course,
for us to try to understand the actual material a little bit more. So, for example, one of the interesting features of having these multinary chalcogenites with multiple options to intercalate 3D metals or group 1, group 2 elements is that when you do intercalation in close proximity to that little, molybdenum 6 sulfur 8 cluster, these intercalants are in close proximity to basically, sulfur p orbitals that you're gonna want to, there's gonna have to be some type of charge transfer happening from the intercalant to these available orbitals. And not only that, that basically has an impact on electron localization surrounding the area where sulfur is in close proximity to molybdenum. And that is actually important because we know, based on DFT calculations, that there's a strong possibility that CO2 wants to bind to the molybdenum centers within the crystalline structure. So again, for us to be able to manipulate the, to manipulate the area in which the binding is going to occur, it's gonna take for us to understand how we could reduce or oxidize this region by manipulation of the electron structure and composition. Right? These are very sort of, qualitative fundamental connections, but that need further exploration and elucidation for us to then be able to translate into a device.
Well, this is the science. This is gaining scientific knowledge, right?
Exactly.
That you need to then develop the application. Otherwise,
exactly,
it's just playing with it until something clicks. But
you're just trying. Okay, doesn't work, right? I mean, and that's not.
The scientist asks why. Why does it work? Why doesn't it work?
Exactly, and actually the latter, why it doesn't work. I'm really happy that colleagues around the world colleagues around the world as well as journals around the world are figuring out ways on how to promote scientists to speak about some of the lab failures in scientific journals.
This is beautiful. I completely agree with you. We never learn from failures because you only publish your successes, right?
Exactly. So yeah, I mean, I really love that point, Paolo, because it's imperative, right? I mean, it's the only way for us to be able. I think it's one way to further solidify how we could leverage each other's results, good and bad, in a worldwide manner, right? Talking about the good and the bad in a succinct and specific way.
Oh gosh, every one of us has been in a situation where you do something that you expect to work and it doesn't. Right?
Agreed.
There's so much learning there, and you never speak about those things. Well, yeah, maybe within your own lab, but that's it, isn't it?
Yeah, it's not encouraged. I think we obviously have ways to go to make it even a much more common practice. Right. But it's really encouraging to see journals supporting it, because I think that is just going to hopefully do a nice ripple effect.
All this is super fascinating, and I wish we had another couple of hours, but I'm sure you have better things to do than spending your whole morning with me. So I have to come to my usual final question of the interview, which is always the same. Kind of makes it nice and comfortable for me, for the listeners, hopefully. It's just now that you've been through your paths, and you're still young and with a bright future ahead of you, I'm sure. But you're also accomplished already, and you have a lot to give, and you're giving. So what would be the one piece of advice you'd give, or you are giving, right, to the people you mentor, so someone just starting their career?
Yeah. First and foremost, no fear of failure whatsoever. Fail often, it's okay. And we obviously in a safe manner, but I think that getting comfortable with the fact that it's okay to fail. I mean, this goes back to the whole of promoting our failures worldwide so we can learn from them. I like to instill that into my core team of students. I want you to fail. It's okay to fail. I want to talk about your failures as well. So no fear of failure. Another big one is you are not your results. Okay, so regardless of what happens, you go into the laboratory, you've been working on a project 1 or 2 years, of course, monitoring progress and whatnot, but these failures that you are, encountering as a scientist do not have to do nothing with the exceptional human being that you are, and most likely scientists as well. So if you can encode that in your brain that you're not your results, and little to no fear of failure, then the next thing you know, you are, you're setting yourself up to have a natural progression of your development as a scientist. And then last but not least, I always like to tell my students that allowing yourself to be uncomfortable is when you truly are winning, right? Especially when you are developing as a PhD student, of course, there are many challenges and a lot of things that you didn't even expect for them to be challenges. So, being uncomfortable with being uncomfortable is actually really helpful as well. So these are all mantras that I constantly I'm implementing to myself as well as reminding to my team.
This is great stuff. Great stuff, my friend. It's been fantastic to speak to you today. I've learned a lot. It's been great fun. Thank you very much. Thank you very much. Congratulations for everything you've achieved so far, and best of luck for the future.
Thank you so much. Have a great one, and hopefully we can continue to catch up in the future.
I'd love to. Look forward to it. Thank you, Mike.
Ciao.